Okay, so myself, Anmol, and I'm going to be discussing the synchronization and locking primitives in OS, Linux OS, and xv6, and what improvements I can make in xv6 so that taking inspiration from Linux OS basically. So yeah, we can see that what we have is why do we need locking and synchronization primitives in the first place? With the new with multi-core architecture being on the rise, all the programs being parallelized, you require a lot of threads and processes to be synchronized. And you'll use locking, you use a lot locking principles and synchronization principles for this, and OS needs to support this. So as you can see, like nowadays processors have becoming very small, so it's easy to fit a large number of processors on the same chip, and peaking processes fast is very hard. So if we are able to make a program very parallelizable, it will have a great performance impact, and hence locking plays a very important part in synchronizing this and affecting its performance. So now looking at locking principles and synchronization principles in Linux versus x86. So there are first of all two kinds of locks, major locks. So these are blocking locks and non-blocking locks. Example of blocking lock is a spin lock, and example of a non-blocking lock is semaphore. So there is also conditional variables. Conditional variables also help us in synchronization. You would have learned about wait. We have learned about wait and sleep in x86. So these are examples of conditional variables. So these three majorly play roles in the locking and synchronization of processes and threads in Linux. And in xv6, we don't have any threads, so we don't talk about the synchronization and locking in threads. But we do talk, but xv6 do support multi-core architectures, so there might be a process on core 1 and process on core 2 trying to access the same thing. So we do have to think about locking and synchronization. So in xv6, we just have a spin lock, and we have a and spin lock is blocking. So it's only more useful in the cases where you have a very small critical section of code because it's simpler. Spin lock is simpler to implement. But if you have a very large section of critical code which is going to take time to implement, we'll see that semaphores will be much more better. So like what are the three major things that I could pick up that were different in xv6 and Linux is first of all that xv6 you only have synchronization and locking functions available in kernel processes for kernel processes and not for user space processes. So that's one thing that we can work on. The second thing that we can work is again extending support for semaphores in xv6. And the third thing is like there are a few specialized lock like reading and writer's lock, read writer latch. You might have heard of it. So these are specialized lock which will give you specialized functions, and we'll learn about it going ahead. So like let's just look at how can we extend the spin lock and the conditional variables such as wait to user space processes. First of all, why does not xv6 do this? Because xv6 for user space processes do not allow sharing of memory. So first of all, if you want to make use of this in user space, you have to also modify x86 such that the user space processes can share memory. So that's something that we won't delve into because my topic is specifically about uh, synchronization locking. But if suppose we implement that feature, then we'll need to think about synchronization locking in user space also. And we can tackle it in the same way as it is tackled for kernel. So here's the example of kernel struct and lock, which you can see. It has a Boolean variable logged, here stored as int, which tells you whether it's held or not, and then few debugging information. And here are the system calls which would look like this. So you would have to initialize the log, then you would have to acquire it. When you acquire it, you set it to 1, and then you have to release it. And you can basically what you will have is you will also having a checking condition. So whenever you acquire a log, you cannot go into the critical section of the log unless acquiring it. So you can create conditions like these, and you can use this in a similar way as kernel processes use. So that's one thing. Moving ahead, what we have is so this was about extending the user space. These spin locks and wait, which is already available in xv6 to user space if the user processes can access the same memory spot, which isn't by default available. But if suppose we make that, the second feature that I was planning to implement is implementing semaphores in xv6. So semaphores is a non-blocking call. So what I'll try to make a difference between blocking and non-blocking. In a blocking call, what happens is like in spin locks, what will basically happen is if the lock is not acquired by one process. So suppose the process 1 is taking place in CPU 1 and process 2 is taking place in CPU 2, and process 2 has the lock right now and it's doing some work. So the process 1 will also try to acquire it and will have to basically what will happen is it will be blocked. So it will be basically wasting the resources of the CPU one, the process one basically, which is not able to acquire the log. So what we can do is, if this critical section gets big and if process takes a lot of time, we can implement a non-blocking lock. What will happen is this will mark the process P1 as waiting, and some other process on the core one can take place instead of process P1. So it will not stop core one from doing some other process. And here semaphores come in. So basically this use conditional variables sleep and wait along with spin variables to actually implement this whole thing. So you have a spin lock, and then you have basically you have a spin lock to basically check the condition of wait and signal. So here I have implemented a binary semaphore. So binary semaphore is similar to a simple spin lock, in which what we basically have is only one person can acquire a lock and only one person can unlock it. So you can have multiple multiple level of semaphores, like n people can take the lock and n people can unlock it. I have implemented a very simple version of it here. So what, as you can see, like I have declared the structure semaphore, it has a waiting queue. So how does it accomplish the non-blocking task is, rather than putting a while loop, which will make the CPU busy, it will basically mark the CPU in waiting wait and put it in the queue. Now this won't block the CPU. So if you put it in the queue, you're basically making it non-blocking. So that is how the semaphore is implemented, and that is what the wait queue that we see is here. So the next we have basically these wait and signal are the wait of similar to acquire and release in spin lock. So wait means it will basically it will say that I'm acquiring the lock. So wait is this way to say that I'm acquiring the lock, and signal is way to say, tell that okay, I have finished my lock, I'm releasing my lock now. So it's similar in that sense. The fourth extension that I'm going to be talking about is implementing a readers writers lock. So what happens in a reader writer lock is, you basically if you have read about the reader writer consumption problem, what you have is you might uh, you might have a file which many readers can read, right? And why should you and if the contents of the file is not changing, you should have a condition where many readers can read. It should not be a restriction. But if you take a simple binary semaphore that I have implemented here, if the readers take a lock, the other reader cannot acquire it, because this only one person can take a lock, another person will have to wait till the first person releases the lock. So this is to overcome that. Multiple readers can basically read from this, but only one writer can write to this. So I've implemented in such way that if there are multiple readers, they will be able to acquire a lock, and I'll be just incrementing the count of readers. So this is a pseudo code here. As you can see, we have readers equal to 0, writers equal to 0, and like as in readers come in, they will be acquiring the lock. And if there is no writer, then only they can acquire the lock. So as you can see, they will first acquire the lock, check if the writer is there. If writer is there, then they will be in the while condition. So this is blocking here. This is the blocking part. And it will be checking till the writer is finished. So reader here is blocked till writer is finished. This is one consideration that you can have. You can also make it this non-blocking by putting it into a queue. That's also one part of an implementation that we can think about. But I have implemented here a very simple implementation. So I have put it in a blocking code where it will be waiting till the the writer unlocks it. So as you can see, if there is no writer, or if the while writer, basically while writer is basically, is there a writer or not? So while writer is there, it won't be able to unlock it, and it will be locked. Then it will be able to unlock, and then it will be able to gain the mutex lock and again unlock it, as you can see. So similarly, unlock is there. So you decrease the amount of readers that are present, and you signal that okay, I'm finished. If there is no more readers, that is readers equal to 0, a writer can start writing. If there is some writer out there, so you signal that, and similarly writer is there. So in writer, you have to keep sure that there is no other writer, and readers are not greater than 0. Basically, there should be no reader and no writer. Only one writer can write. Only then the writer will be able to acquire the lock. So writer.lock is about acquiring the writer's lock, and writer.unlock will signal that if someone else is there, be it the reader or a writer, he can acquire the next lock. So I think that's it for the improvement. So I have suggested 3 improvements: a user space extension of the existing spin lock and wait and sleep conditional variables, implementation of semaphores, and implementation of a reader writer block. So thank you for listening to me.